Relative velocity application is what we are starting now, and we are considering river crossing. When we are crossing a river, this can apply to airplanes, right? When they are moving in air, they usually cross the air that is blowing in a particular direction. So they consider all these things, the velocity of the airplane relative to the air, before they consider moving in a particular direction and at a particular time. But to simplify things, we are going to look at such an example, such a case when we are simply crossing a river. Either we are swimming to cross a river and get to the other side, or we are in a boat and then we are cruising the boat in a particular direction or particular way in order to reach the other side. We have to also keep in mind that as we are moving the river is not stationary. It also moves with its own velocity. So you moving to cross the river or you swimming to cross the river, and that of the yeah, meaning you are going to deal with your velocity and you have to deal with the velocity of the river, so that you can know when and how to move in order to reach a place you want to be, right? So we are going to start with some questions, and this is the first question that we'll be looking at. The question says, a boat crosses a river, crosses 5 kilometers wide in 30 minutes in still water. The river flows at 4 kilometers per hour. What is the resultant velocity of the boat, and what angle does the boat make with the direction of the river flow? So I'm going to give a scenario here. So you see, let's say this side is bank A, right? This is bank A, and this is the other bank of the river. This is bank B, and the river is flowing here. The river is flowing here. So it can be, let's say, okay, let's say the river is flowing in this direction like this, towards the east. And you are here, and you want to move to this place directly here. You want to move from here to here, right? We want to how do you call it, reach here exactly. You want to exactly reach this place when you start jumping into your distance. But then we know that in still water means that when the river is not flowing, or when the water body is not having any velocity, when the river is not, or the water body is not applying any velocity, right? You have a particular speed of swimming speed, or if it's a boat, you have a particular boat speed in crossing a river. That's when we did still water. So whatever they are saying in still water is just meaning that, okay, when the river is not applying any velocity or flowing, or the water is not flowing, this is the maximum that you are usually flow. So in this question, you have a similar case. Coil is 5 kilometers wide in 30 minutes in still water. So I'm going to consider still water here. And so this person will move from here to here without a problem. The boat will move from here to here without a problem, because the river is not flowing in any direction, any velocity. So the water is stationary. That's still water. That is still water for you. So you use still water values in order to determine the actual velocity of the man, the actual velocity of the man, so or of the boat. That's all you use. So we have 5 kilometers wide. That's the If it's a still water is 5 kilometers wide, this person can cross it in 30 minutes. So the time is 30 minutes. So T is equal to 30 minutes. So first we are trying to determine the velocity of the boat, right? In still water. 5 kilometers. We know that velocity is equal to what? Distance over time, right? Or displacement over time, right? Displacement over time. The displacement here is 5 kilometers. That's going to be 5,000 meters over 30 30 minutes. That's 30 times 60, right? So let's solve this and see. Yeah, so we have 50 over 18. This one, let's put it in a calculator and see what we can get. Um, 50 divided by 18, 2.777. So I got I can say 2.78 meters per second. So we know that the velocity of the boat is equal to 2.78 meters per second. So because the clue from the still water side is what we use to find the velocity of the boat. When there is no velocity of the river, the water body is not applying any velocity. Okay. But then that's what we know for the boat, that in still water, it basically moves with this velocity. But now it's encountering a river that is having its own velocity. And they say the velocity of the this thing is 4 kilometers per hour. Wait, this the velocity of this is 4 kilometers per hour, right? And what we have is meters per second. So let's go back and just quickly do make sure that we get everything in kilometers per hour. So we have 5 kilometers. Let's evaluate this thing again to get it in kilometers so as to make things easier for us. And 30 minutes, right? 30 minutes, that's half an hour. So that's half an hour. That will be 0.5 hour at the bottom, right? Then you have 10 kilometers per hour. So this one is actually 10 kilometers per hour. Let me clean this in. You can decide to change this 4 kilometers to this thing, but it's just best to just have it kilometers per hour. Make sure the units match. That's what we just try to do. We don't look at that. So yeah, I'm trying to expose all these minor things that we have the error, so that when you are solving, right, you keep in mind, you learn from it, and then you see that that's how it's actually applied. So 10 kilometers per hour, and then against 4 kilometers of for the river. Now how do we solve it? So we want to move from here to here directly. That's what we want. But note that we are no more in a still water. We are no more in a still water. We are in a flowing river. So when we are the velocity, the river will pushing us like this, while we also be moving down like this, right? But at the end of the day, because of the pushing, right, you may not actually reach here, because when we start, the river will push you small, small, small. You also be trying, you pushing you small, 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 small. You be trying to come, the river will also be pushing you, pushing you, pushing you, pushing you until you reach here. You actually land here. Exactly. That's when you actually decide to enter the river straight and move. When you are moving, right, we are going to exhibit or experience a resistance from the river due to the velocity. So while you are doing like this, right, even though your velocity is higher, but the river will be pushing you small, 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 small. So it won't allow you to exactly come here directly from here. But at the end of the day, you are going to reach a point here, right? That's what's going to happen. That's what's going to happen. At the end of the day, we have a right angle triangle. So this is the actually resultant. The resultant velocity will be this one. So let me represent this here. While you are trying to come from A to B, you actually land at C, because the river is flowing like this. So the river will be pushing you while you are also coming down. So at the end of the day, this is the resultant velocity that you guys see. So you actually reach here, and now you have a right angle triangle. So this one is down, and the river is flowing this direction. So you have these things for you. Okay, so this is what we have from this river case. And do we know the velocity of the man? This is the velocity of the man. We have 10 kilometers per hour. The one moving like this is the reverse velocity. That's 4 kilometers per hour. We can use this data to evaluate VR for a right angle triangle. So for right angle triangle, we say that the VR is going to be equal to square root of velocity of the boat squared plus velocity of the river squared. River is small r, so that I can make the difference. Velocity of the man squared, right? That was 10 squared, plus velocity of the river squared was 4 squared. So if you do this, you are going to have 100 plus 16, then you have square root of 116. So square root of 116. Now calculator, let me quickly do that for you. 116. So I got 10.7703. That's what happens actually. That's what we got. Actually, 10.0 kilometers per hour. That's the resultant velocity that we got. Right? It means that that's the velocity that you actually see the man moving. Velocity of the river relative to the man. Basically, that's what we have. Okay. Um, but then we're also interested in the direction. When it's moving, right, there will be a particular direction here, theta. We actually want interested in that direction that we finally be moving in. And then we know that this is theta, right? This is theta, this is the side, this is the opposite side, and this is the adjacent side, adjacent and opposite, right? How do you find theta? So you know adjacent and theta, so you're going to be tan theta, SOHCAHTOA. Remember that opposite over adjacent. The opposite was 4, and then the adjacent was 10. So what we have now is theta will be equal to tan inverse of 4 over 10. 4 over 10, that would be like 2 over 5. But let's do that in the calculator. Tan inverse of 4 0.4 basically 21 point. So I got theta to be 21.80 degrees. So let me draw the diagram here again. So over here it will be moving 10.77 kilometers per hour. This one is 4 kilometers per hour. That's the river, and the river is flowing like this, and then this guy is moving down. What do we have? 10 kilometers per hour. And at the end of the day, we have to need this theta. So the bank is here. You know, the bank is here. The bank of the river is this side. So the velocity relative to the bank will be what? So this is between the body and the resultant, right? But between the body and the resultant will be somewhere here. And you know the total angle is 90 degrees, right? Total angle is 90 degrees. So this velocity that we found is the velocity between the body and the resultant, right? The original direction that is supposed to take and the resultant. But if they ask for the velocity between the the man, the relative velocity of the man and the bank of the river, know that from here to here, as well as from here to here is 90 degrees. So if you know this particular portion, if you take it out of 90 degrees, then you'll be able to get that particular velocity angle that is relative to the bank. So here this is 90. So I'll do 90 minus 21.80 degrees. So when I do that, I'll be able to get alpha. Alpha, which is the velocity between the man and then the bank of the river. So let me do that. I have 90 minus 21.80 degrees. We have 68.2 degrees. So finally, this is how the man moves. The man is now seen to be moving with a resultant velocity of 10.77 kilometers per hour and in a direction 68.2 degrees relative to the bank. This one, this direction is relative to the bank, right? The bank of the river. So let's say bank A. Okay. Yeah. This is how to go about solving that. So basically, crossing the river is going to show a case of um, right angle triangle. We have this question for you to try as well. A swimmer crosses a river 3 kilometers wide in 20 minutes in still water. The river flows at 1.8 kilometers per hour. What is the swimmer's resultant velocity, and what direction does the swimmer move relative to the river bank? River bank, right? We have to remember all that. So try this thing while we solve it in the next session for you. But then solve it for now. Let's see how you can do that. Let's see the next session and see the solutions of this particular question.